Hello, hello.
Hello, hello.
Oops. Test, test. Sounds fine. Okay, good. Cool. Interesting. Today it's somewhat sparser, even though this is going to be the first class that doesn't talk about just math. Well, I guess we're just going to start. Well, actually, this is going to be a very exciting class, at least for me. So I'm happy that you guys are here. So today is going to be the first time we're going to talk about basically some deep learning, and this is kind of the first lecture in the module 3D scene representations and differentiable rendering. And this lecture is brand new. This is the first time I'm giving it. I made it over the last few days. So if it's lacking some refinement, please let me know all bugs afterwards, and yeah, work with me here. So if you have questions, please just ask. Okay, now people are coming in. Okay, so usually we start at 2:35. Cool. Okay, so first a recap. Last time we talked about epipolar geometry, and one reason why I'm excited about the class today is because we're going to actually use this. This is going to be highly useful today. And just as a reminder, what is an epipolar line? And we'll just give names to all of these things one more time to go through them. So what was this point called in the past? Someone, you can just call it. Right, that's the camera origin. What were these points here? So this was the camera origin projected onto the other image plane. Epipole, exactly, epipole. Then what was this line called? Epipolar line. What was the plane called? Epipolar plane. Sorry, it's good. Cool, good. And so what was the purpose of the whole epipolar line shenanigans? The point was to get some math to figure out if we have a stereo system or any multi-view system, how can we find the correspondences of a point of a pixel coordinate in image number 1 to pixel coordinates in image number 2. So one view of epipolar lines is given a pixel coordinate in image 1, the epipolar line is the line on which you have to search if you want to find the corresponding point in image number 2. That is one view that we're actually going to take today to solve a practical problem in disguise. Cool, so that was epipolar geometry. Then we also talked, this is not something we're going to use today, but I just want to bring it up one more time. We talked about the fundamental matrix, which is basically the linear map that encodes all of the epipolar geometry in a single matrix. And just as a reminder, the fundamental matrix is actually the matrix that maps a homogeneous pixel coordinate to the equation of a line in the other view. So for instance, if you have a homogeneous pixel coordinate x1 tilde, then you can multiply it with the fundamental matrix, and you'll get out the three vector that encodes the line. And it's a homogeneous line, so it basically gives you the parameters of the implicit equation that all of the points that you slot in there, and they give you 0 lie on the epipolar line. Make sense? And we use this fundamental matrix to talk a little bit about how you would go about solving for the pose if you had correspondences and stuff like that. And then the key insight from last lecture was if you actually have to do that in real life, try it with CallMap. Has anyone actually done that since they went home and tried using CallMap? Okay, maybe we actually will do this as extra credit for the homework. I think it would be fun. Everyone should be trying to use CallMap. Cool. Any questions that you want to ask again, or anything that you want to bring up again on this highly engaging topic? Great. Then we can move on. Bundle adjustment. This was, the CallMap point. So a bundle adjustment is just like an expression for like casting 3D reconstruction and camera pose reconstruction as one big, real big optimization problem. where you just solve for both the camera parameters and the 3D point cloud at the same time. And we briefly just touched upon it, and as I had mentioned, if you want to get deeper into that, use Colmap and like just play around with Colmap. This is, I think, actually the output of Colmap. So cool. Then actually, this was the slide I had searched for in, I think, the second lecture. We talked about camera coordinate conventions, and some of you might know this paper called neural radiance fields. The funny thing was that, as in many papers, the NERF paper, I don't want to single it out, but as in many papers, the authors, when they wrote the code for it, were themselves confused about camera conventions, or were like, oh, I don't know, they like hacked around like some practical thing. And so NERF, the NERF data loader that you see here, they did this thing where they were using a data set called, from a paper that they had written before, which is called LLFF. I don't actually remember what the full title is, Local Light Field Fusion. And that one had OpenCV poses, which we discussed. OpenCV convention is the top left corner of an image is 0, 0. X points right, Y points down, Z points into the image plane. That makes sense. Then they, in their data loader, converted it into some coordinate frame that no one understood, like some complete new convention. No one had used it before. I guarantee you this has wasted hundreds of human hours, because people probably looked at it and was like, what is this? Or they tried using it for another paper, right? Maybe they were like, oh, great, I'm going to use this data set with the data loader in my own project. And then they assumed it was OpenCV camera poses, but it wasn't. And then who has started with homework number 1? Oh, a few people. So if you have started with homework number 1, then this will be a problem you'll be firsthand confronted with. So it's not a made-up problem. Yeah, and then afterwards they converted it to OpenGL poses, which is yet another camera convention. Okay. With this in mind, today we're going to talk about the first instance of how you go from images with neural networks to some representation of a 3D scene. So like just as a reminder, one motivation we had for the whole lecture was kind of this image. Machine learning for inverse graphics is the title of the lecture. And we have graphics, which basically graphics tells you how do you get from a 3D scene plus light sources, like materials, geometry, light sources, and so on. Graphics gives you the model that allows you to simulate how light bounces around and how then images are formed on the image plane of a camera. So that's computer graphics. And then inverse graphics is this process of going from the images to like some 3D representation of the scene in a data-driven way. So like you use machine learning, you use experience to figure out the image that I'm seeing, what is the underlying 3D state of the world. And that's the first time we're going to talk about this today. The simplest version of this. And then downstream tasks comes later. Okay, good. So that's some motivation. And today, specifically, we're going to talk in a way about the simplest possible way how you can parameterize 3D scenes and how many people actually, many of you have probably actually interacted with them before in computer vision. Namely, today is all about 2.5D representations or depth maps. So we already mentioned depth maps before. Maybe you remember this picture. So this is a picture from a scene captured with a Intel RealSense. So Intel RealSense is an RGBD camera. It gives you an RGB image, and for every pixel, it gives you a depth. And you already saw this image, actually, where we discussed, well, actually, given the RGB and the depth, you can actually go to a point cloud. And if you think about it, right, the point cloud, in a way, like this process of going from an RGBD image to a point cloud, or like the point cloud is the first kind of 3D representation you could possibly think of. It's like, in many ways, the simplest representation of a 3D scene you can think about. So we also skip this. And actually, let me talk about this. So the funny thing with depth maps is, so now how does machine learning come into this? We also already mentioned this. So we did mention that there are cameras, just like the one that I just showed you, that can measure depth directly. For every pixel, they give you a measurement of the depth. And we're not going to talk about how these cameras work. It's interesting in its own right. Well, actually, one of the ways in which this can work you already know about, which is stereo depth estimation. So you already know if I give you 2 images of a scene, you know of one way how you can get the depth for every pixel, right? But so this is actually relatively a common modality, so you can just buy these depth cameras. And so what people then did, of course, and this is the first thing we're going to talk about, is monocular depth estimation. So I'm sure you have probably all heard about monocular depth estimation before, right? Who has heard about monocular depth estimation before? Okay, not everyone. Who has used a monocular depth estimation method before? Much fewer. Okay, good. So what is monocular depth estimation? It is the first deep learning thing we're talking about. It is going from an image, stick it into a neural network. The image gives you the depth for every pixel. That's monocular depth estimation. And this concept is fundamentally very simple, right? So let's talk about the simplest way of doing this. The simplest way of doing this is realizing that because we have depth cameras, we can just capture ground truth depth for a bunch of scenes in the real world. So we can just take these depth cameras, we run around the real world, we capture these depth observations, great. And in that way, we can just capture a data set for supervised machine learning. It's kind of like, this is kind of machine learning from 8 years ago. So we just run around, we capture a bunch of data. And when I say from 8 years ago, I literally mean 9 years ago. So one of the first papers that you could say is like 3D computer vision with machine learning was this paper, depth map prediction from a single image using a multi-scale deep network. So I think this is a good little excursion. There's a few good insights in this paper. This is considered a seminal paper. It has, I think, 2,500 citations, something like that. A few things to notice. So I just pulled this figure here from the paper itself. I hope all of you are familiar with convolutional neural networks and deep learning. Is one of the prerequisites of this class, right? But this is how deep learning papers looked like 9 years ago. So what you notice is this is the number one figure in the paper, and the number one figure in the paper shows the architecture of the convolutional neural network. Because back then, that was always a contribution for the paper. People were like, okay, contribution number one, we conceived this new neural network architecture. We plugged together CNN modules in a novel way that no one has seen before. And so let's just briefly go through this, right? They basically had this coarse and fine stream. I actually don't know if they claimed this as a contribution, but I'm pretty sure they did. If you look at the contribution of the paper, they're probably like, here's a coarse and fine stream for like this task. Okay, so what does coarse and fine mean? Coarse just means that they have, which I don't think you would do this way today anymore, but coarse just means they have the full resolution image, and then they just have pooling, like downsampling, basically convolutions that give you a one-by-one image, I guess, and then they upsample the one-by-one image to a depth map, and that one is coarse because, of course, it's going to have like very little detail because you have this huge bottleneck of going to a low-resolution representation. And then there was the fine path, which doesn't downsample the image, and I guess the reason why they did it back then is because it was too expensive to do something that would like integrate this properly. And then they had these tables in the paper back then, like here's the architecture of the CNN. No one does this anymore, right, in machine learning papers today. Okay, but then what did they do? They took this architecture, they built it, and then they just trained it on data set that they collected themselves. And this is pretty good back then. So like this is what it looked like. So here on the right hand side you can see ground truth. So you can see the ground truth depths that they collected with a depth camera, I think. And then on the left you can see the input, and this is the output of the coarse model. This is the output of the fine model. Later in the class, we'll actually talk a lot about coarse, about why this looks the way it looks like. This is actually something that is non-obvious. But anyways, you can kind of see not really any fine detail, but we kind of not unreasonable. So here's the first neural network that goes from a monocular image in a purely data-driven way to depth estimates. Okay, so what's there's a few catches of this. Like the first catch is that you can call this ground truth depth, but in reality, of course, the depth doesn't look very much ground truth at all. So if you use any of these depth sensors, this is what the depth maps look like. And you can see there's lots of holes. The black stuff is just holes in the depth map. The depth map is rather noisy. The boundaries aren't clear. So the first limitation of these monocular depth estimation networks is that actually the ground truth data isn't that good in the first place. And this is something that people had struggled with. And so this is actually a very active area of research today. This is considered one of the branches of like 3D computer vision that work really well. Like it works well enough that in practice you can use this and you can make the assumption that you have a well pre-trained monocular depth estimation network. And we're going to talk a little bit about what were the changes that made it possible, because some of them are important considerations. And one of the biggest changes that were necessary for getting from what you just saw, which is like not bad, but clearly far from like satisfying, to something that looked much better was basically scale. So to train neural networks that generalize well, you need lots of data. So we already discussed how you can collect these data sets, but even with RGBD cameras, it's still kind of expensive, right? You still kind of have to run around and you have to capture these data sets by hand. And it turns out that over time, there were a few people that have actually put the effort in and collect these data sets. And so this is a table from the paper Towards Robust Monocular Depth Estimation. And so they basically just made the summary of like, look, here's all of the data sets that are available for the task of monocular depth estimation. And so the thing we're going to want to look at, because it tells you a lot about the state of the field. Note this is from 2022, so this is just from a year ago, right? So this is really still an active area of research. The thing that we want to look at is like this little box here. So there's annotation and there's depth. And what do they mean by annotation? They mean how was this data set collected, right? So like how did the people that collect this data set get the ground truth depth for this data set? And then the depth, here they denote whether the depth is like in metric or whether it's like arbitrary scale and stuff. And let's look at this table for a moment and see if we can explain what is happening with what we have learned so far, right? Okay, so annotation RGBD. So there's this one data set, Dimmel Indoor, collected with an RGBD sensor, and they say the depth is metric. Okay, that makes sense. If you build an RGBD camera and you can calibrate yourself, you can calibrate the sensor to give you a metric depth, which just means that the depth values are actually in meters, right? Makes sense. Okay, let's look at the next one, structure for motion. Okay, so the second line is structure for motion. Structure for motion is CalMap, or one of these structure for motion things that we talked about in the last lecture. And here you can see an interesting little bug, which it says no scale. So let's talk about that for a moment. It turns out that when you reconstruct scenes with structure for motion, you can reconstruct the camera poses and you can reconstruct approximate geometry from videos. The problem is that the reconstructions you get are only up to scale. So in practice, what that means is the algorithm might give you depth maps and poses, and they can all be scaled by any scalar, and the reconstruction will be equally valid. They're all minima of the global optimization problem that is bundle adjustment. So what that means is you might think about, oh, I'm just going to go around, capture a bunch of video, and then from that video I can build a huge data set for monocular depth estimation with structure for motion, and that is a great idea. The problem is just that when you do that, each of the depth maps will be scaled by an arbitrary number, which you don't know how to figure out. Okay, so that's apparently a problem. So, and you can think already about why that is a problem. We're going to talk about it in a moment. Then there's stereo, and there similarly they say, oh, the stereo camera doesn't have scale and it has shift. So that is probably because these data sets were, so you can see here this says like something like red web. So these might be stereo cameras, but when people computed the depth on top of these stereo cameras, they probably didn't have access to the camera calibration and stuff like that, so they don't actually know what the scale of what the baseline is, and so it's not calibrated. So long story short, these are basically, actually these were the data sets that this paper proposes to train on, because these are rather big. You can see on the left side number of images. The number of images is pretty big here, 220,000, 130,000, 1.5 million, like really big, but none of them are metric, basically, or like very few of them are metric. And then on the bottom, these are all the ones that are metric, and they want to use these as test set, because for the test set, you want to benchmark it with metric depth. Okay, so let's talk about why is it a problem that all of these data sets have different scales. Why is that a problem for monocular depth estimation? I mean, maybe one of you can take an educated guess. Why would that be a problem? So you just supervise deep learning, image in, depth map out. Why would it be a problem if the depths would be arbitrarily scaled?
Why the network not actually learn the real depth and average between all the different scales that is present in the data set?
Genau, yeah, exactly. Sorry, genau. Genau is a German word, means exactly. Exactly. So you're kind of screwed. If you train your thing with regression, so you just tell me, oh, for every pixel you regress a depth, but you don't know the scale of the data set, or you don't know the scale of that particular scene, what is your neural network going to do? It can't guess the scale. There's no way. The scale is, especially in structure for motion, the scale of every scene is arbitrary. It's literally arbitrary. So you can't look at the image and decide the scale. So what gives? Like, how could you still train a neural network on this thing? So the first thing that people came up with, and this is actually from this original paper from Eigen et al. In 2014, is coming up with a scale invariant loss. So they basically said, okay, we want to train our neural network, and we want to train it on this data set where we don't know the scale of the data set. What we're going to do is we're going to build a loss that is just invariant to the scale. So our neural network is going to output something, and the output is going to be compared to ground truth up to scale. So if the scale is wrong, our network doesn't care. And how does that work? The way it works is that the way it works is that you do the comparison in log space. So y and yi asterisk, y and y asterisk are the ground truth and the predicted depth map. So you compute the log of the two. And if you think about the scale factor would then be pulled out as a additive factor, right? And then they say, oh, and then we're going to have this alpha y asterisk. And the way that we're going to, and what we're going to do is we're going to compute alpha y and y asterisk as the least squares fit of like the, so they basically just, they look at the prediction, they look at the ground truth depth map, and they just compare the two and they ask what is the scale factor that aligns them the best. Then we're going to scale one of the depth maps by that factor, basically, and then we're going to compare them. So we pull out the scale, and we say the neural network doesn't have to care about the scale. Does that make sense? Questions? Cool. So scale invariant loss, that was the first thing that helped. Then there is another problem, and like we're really just going through all of the things we learned so far. So I told you this is kind of important stuff if you want to do a good job at 3D computer vision. When we talked about the first two lectures, we talked about the intrinsic camera parameters. So the intrinsic camera parameters play another important role, which is that scale invariance is actually not enough. So structure for motion gives you keeps the scale unconstrained. It turns out for many of these stereo depth estimation data sets, there's another funny effect, which is that the way that the cameras are calibrated in these setups is such that there is a global offset on the disparity. So basically the stereo depth estimation pipeline, the stereo depth cameras, they give you a stereo image and then they compute disparity. And for a variety of reasons, for instance, because these were built for virtual reality setups, it is convenient to like add an additive factor to the px and py, which is the image center offset, that is specific to the scene, or that is specific to a certain camera setup. And it turns out you don't know that calibration. So for many of these stereo data sets, you don't actually know the correct camera intrinsics. And what that means in practice is that there is a global additive offset on the disparity of the stereo image. And you don't know it, and so it's basically, that's another big problem. So this paper in 2022 proposed, okay, we need to go further than the scale invariance, and we're also going to add shift invariance. So we propose to perform prediction in disparity space, inverse depth up to scale and shift, together with the family of scale and shift invariant dense losses. So let's talk about disparity one more time. I hope you remember this little setup. So this was from the very second lecture. From the second lecture, we had the stereo depth setup, and we introduced the concept of disparity. And just for the record, what is disparity? Disparity is if you have a stereo setup and you have a 3D point, and you project that 3D point onto both of the cameras, the disparity is the distance in pixel coordinates. So it's the difference between the pixel coordinates of the same 3D point projected onto the two cameras. That's disparity. And in practice, the disparity looks something like this. And now here you can see, so this pixel coordinate, right, is a function of the focal length and of this image center, right, this px, py in the intrinsic camera matrix. And this is exactly the thing now that you don't know, and that might vary. And so that leads to like a global offset in the disparity. And just for the record, right, the disparity image looks like this. It's like the disparity is inversely correlated with the depth, right? So z is the depth, this is the disparity, so the disparity is the inverse of the depth up to scale. And this is what the disparity image, for instance, looks like, right? So things that are close have large disparity, which just means that things that are close move more when you close one eye versus the other, right? If you like look at something and it's close by and you open and close one eye, then you see that things that are closer to you move more. That's because they have more disparity. And then the depth is exactly the inverse disparity. So the depth would look opposite to this, right? Okay, so how did that paper deal with that? So they were like, okay, we need to fix that as well. And this is like just the reality of dealing with real-world data sets and the reality of 3D computer vision and camera calibrations, right? So all of the stuff we talked about in the first lectures. They proposed a scale and shift invariant loss. And now actually the way they did this is a little bit smarter. So this is just pulled directly from the paper. So they say, oh, we have a scale shift invariant loss. Takes two disparity maps as input. D hat and D hat asterisk are disparity maps now. So these are basically inverse depth up to scale thing. And then they say, okay, we're going to have some loss on top of these D hat things. And now the question is, how do we get D hat and D hat asterisk such that they are such that this loss becomes scale and shift invariant? And the answer is very simple. It's kind of similar to the eigenpaper, but now in disparity space. So they basically do the same thing. They say, okay, let's take the ground truth disparity map, and let's take the predicted disparity map, and then let's just solve with like a little least squares problem that's just solve for the optimal scale and the optimal translation to like fit these two against each other. Then we use that scale and that translation to rescale the prediction, and then we compare the rescaled version to the ground truth version. Does that make sense? Does it make sense? No. Okay, good. What's the what is confusing? Please feel free to ask. Since this is the first time I give this lecture, I anticipate that it'll be a little bit short, so we have a little bit time for discussion. So if you have questions, please ask. So does the motivation make sense why we have to do this? Like, why do we have to build these losses that are scale and shift invariant? Yeah? Okay, so did it make sense? Does this general idea make sense? Like we have the prediction of the network. So di hat is literally the output of your neural network. So your neural network predicts a disparity map. So for every pixel, it predicts how much disparity you would have if you would like place another camera close to it. Okay, so that's the output of your network. And now we need to make the loss invariant to the scale and the shift. Because for all of these real-world data sets, you don't know the scale and the shift of the depth maps because they're all computed with different sensors. Sometimes they're not even from sensors, but from structure for motion. So people took videos and then they used structure for motion to get the depth maps. Okay, so that's the motivation. So questions? Yes? Great question. So the question is there an issue with backpropping through the least squares fit? This is actually a very good question, and maybe this is a point of confusion. So this is actually not this is not something that we will backprop through. So this is very unusual. I think this is fairly unusual. I don't see this very often in supervised learning. Like this correction that we do here, we kind of do it out of the loop. So we take the prediction of the network, and we take the prediction, we look at the ground truth, and we just regress the best scale and the best translation such that they are as similar as possible. But then we don't actually backpropagate through that because you don't have to. All you want is that what will happen is that the neural network will get gradients to the neural network. In a way you can think about it as like outputting relative depth. It's kind of outputting like it's outputting disparity values at different pixels such that if you rescale them and shift them by some unknown scale and shift, then they will be correct. So in other words, the neural network is just saying, I'm giving you a depth map such that I guarantee you there exists a scale and a shift, such that if you scale and shift this disparity map that I predicted, you will get the correct metric depth, for instance. But you don't actually know what that scale and shift is. Make sense?
So you're just like solving for acting like you're part of your network.
Yes. Exactly. So you're just solving for SNT, and then you're like, what do you know? You're just going to use these as like we're going to scale the output of the network like this, and then we're just going to forget this ever existed. In this way, the network only gets the gradients that basically tell it to get the correct relative depth pixel to pixel. So the network is actually predicting relative depth. And if this seems like to be a minor point, it really isn't. I can tell you because we are doing research in my lab where this is a huge problem. So it's like it's kind of David can tell you more about that, or maybe not. So this is actually really annoying. Good. Does this make sense now? Kind of intuitively? Okay, good. And it's actually, if you think about it, it's really weird, right? Like what does it even mean for the neural network to output relative depth? It's like kind of a weird thing. And we're going to talk about an implication of this, which maybe you have already skipped forward to, but it's actually kind of important to appreciate. Okay, so this is a paper from 2021, Vision Transformers for Dense Prediction. Okay, I must have a mistake. I think this paper can't be from 2022. I think they probably published it in 2022 at a conference, but it was an archive in 2020 because this paper is follow-up work to that, and this one says 2021. So I'm pretty sure that the other one was an archive in 2020, and they just got it accepted to a conference in 2022. Anyways, so now we're in vision transformer land. So people are like, okay, so we have the supervised problem. In the past, we solved it with convolutional neural networks. We have this new hammer. It's called transformers. Let's hit it with the transformer hammer, see what happens. So that's what they did. They took an image. Who has worked with vision transformers before, or with transformers in general? Okay, good. We're not going to talk about them too much in this class, but just that you have heard about it before, what you do, what does it mean to be a vision transformer? Who knows how transformers for natural language processing work? Okay, so you have heard about that, right? Like transformers, tokens, like self-attention, all that shenanigans. So it's kind of the same here. You take the image, you split it into patches. So this is what this shows. You take an image, you split it into patches. Each patch is like 16 by 16 pixels. Then embedding just means you have a linear transform for each of these patches, which gives you some like high-dimensional feature vector. So what you end up with is like you take this patch, it's like 16 by 16, you flatten it, and then you have a matrix that takes 16 times 16 to, I don't know, 1024. That's the embedding for each of these patches. And then they add, then in vision transformers, you also add another token. We're going to forget about that. And then you stick it into self-attention. You just do lots of self-attention on top of it. And so this paper was like, okay, no, now we're going to use the vision transformer for molecular depth prediction and for other tasks. And they basically, I just want to go through this so that you know how this looks like. What they basically say is, okay, we stick it into a transformer. And the transformer basically gives you a new value for each of these tokens. So it gives you a new value for these, in this case, 4x4 tokens. So for each of these patches, you will have now a feature. And now the question is, how do you build this such that in the end you get a molecular depth out of it again? This is just one way of doing it, which they proposed. But actually, this is a reasonable architecture that if you wanted to use a vision transformer in your work, this would be a reasonable architecture to use. They basically say, okay, we're going to have like this reassemble block here that then allows us to predict a full resolution image out of it again. Let's see how that looks like. Basically, what you do is you take your 16 by 16 patches. You take your patches, in this case like 4x4 patches. Each patch has a token. And then you basically just concatenate them to something that looks like an image. So you concatenate them to basically what is a 4x4 image. And then you just upsample it with like a learned transpose convolution or something like that. So you basically take this 4x4 image, you like concatenate it to something that is like actually a 4x4 image, and then you stick it into like something that upsamples it, like a learned neural network to upsample it, and that gives you then the thing that is at the same resolution as the input image. Does that kind of make sense? Okay, cool. This is actually something that is just a new way of doing it in vision transformers. It's very similar to like upsampling and downsampling in convolutional neural networks. Okay, I'm just giving you an idea because I thought this was funny when I read this paper because like in some ways, I guess our papers haven't changed that much because from 9 years ago, we had lots of these figures in our papers where we discussed this is what our convolutional neural network architecture looks like. Now we have lots of figures in our paper that say this is how our transformer architecture looks like. So kind of same thing. And then they basically do some fusion, which I'm going to talk about. The thing that is important to look at is the depth maps that you get out of it. And this is starting to look quite good. So remember the depth maps you looked at from 9 years ago? So this is the depth maps you get out of this from 2 years ago. So stuff is starting to look pretty good. So Midas is actually the paper where I said the paper must have come out before. So this was this is the paper from 2020. This is what the depth map looks like here. And then they proposed two different models, which we're not going to talk about. The hybrid one basically has some ConvNet parts, and the large one is just a transformer. And as you can see, the large model. Actually, honestly, on this picture, it looks like the large model is doing a little bit better, but who's to tell? And also notice that these pictures here don't have ground-truth depth because I guess they just use them for qualitative evaluation. But the long story short here is I'm pretty sure if you took a picture of this scene right now and ran it through this network, it would give you something reasonable for most of the pixels. It would be pretty okay. Here's some failure cases, though. So like this is not a solved problem. So my favorite example is the penguin. So here you have a penguin, a bunch of penguins here. And you can see the penguin has its little wings. And the network basically makes a mistake in reasoning about the depth ordering. So the network looks at the penguin, and then it judges that these wings are apparently part of the penguin in the back. And so it predicts the depth wrong, right? And so this is also interesting because if you use these molecular depth estimation networks, these mistakes happen quite a bit. So like there are often like, if you look at them really closely, oftentimes there's still bugs and mistakes. And it's also funny to notice this is not a mistake you would generally make, right? You would look at this image and you'd be like, okay, yeah, this is, no. Okay, so far from solved, but definitely in the realm of useful and something that you can kind of trust works 70% of the time. So pretty cool. Okay, oops, what happened now? Okay, so we're not entirely done talking about this, so we're going to get back to it, but any questions so far? So far, yeah, please. Yeah. So explain to me exactly again what you mean. But you mean you take your ground truth depth maps, and then you just take the maximum of the ground truth depths?
And like normalize all the depths.
Or the highest depth value. And then, yeah, I don't think that fixes the problem, because then you have just scaled all of your ground truth depth maps by like some number, right? But like but within your ground truth data set. Oh no, you mean you rescale all the depth maps such that the maximum depth is always the same. Okay, so yeah, that is unfortunately also problematic, because like sometimes you might be standing in a room and I'm looking at this table, and sometimes you're outside and there's something really far away, right? And then you'll just have rescaled this depth value to be the same as the thing that is really far away. And your neural network again can't. I guess now your neural network knows that the maximum depth should be the same. So in that sense, I think it might help you a little bit, because now your neural network knows, aha, the maximum value, I'm always predicting this maximum value. So yeah, I could imagine that it would do something. My guess is that the neural network will not have a good time, like basically learning this exact rule, because like, but honestly, could be worth trying out. If you want to do that as your course project, I think that would be a reasonable course project. Maybe they even tried it. Maybe you can find something in the literature about this. Yeah, no, good idea. Okay, good question. Other questions? Good. So we're going to get back to molecular depth estimation in a moment, but first we're going to talk about stereo depth estimation. So we kind of talked about this a little bit already, where we talked about like, if you have correspondences in like you have, okay, sorry, what is stereo depth estimation? Stereo depth estimation is you have two images and now you want to get the depth, and you assume that you have the camera pose. And we kind of talked about this in the first lecture, but we actually only talked about it in the case where you have correspondences, and from correspondences you can do triangulation, but the correspondences are like sparse. You have to find correspondences first. So here's one interesting algorithm that is really good to know about for getting for stereo depth estimation. This is an old algorithm. It's actually, I forgot the citation here, but I think it's from 1995. So really old. And the algorithm is called plane sweep volumes. Has anyone heard about plane sweep volumes? Excellent. It's a really neat algorithm, and it's going to relate to our epipolar line geometry shenanigans. So what is the idea of plane sweep volumes? The idea is, okay, imagine you have two frames, and you know their intrinsics and extrinsics camera parameters. And now you want to estimate the depth in the coordinate frame of this camera. How are you going to do it? What plane sweep volume says is the following. It says, okay, let's just discretize the depth space. So let's take the camera frame that we're in, and then we're going to discretize the depth space. Like, I don't know, in this room, maybe you would say far plane. So the furthest is maybe 10 meters, and the closest is like, let's say 50 centimeters. And then we discretize it by like 20 planes. And then what we're going to do is we're going to take our second stereo image, and for each of these depth planes, we're going to warp this image onto each of these planes. And we discussed about depth warping before, right? But you basically say, you can think about it like this. For each of these pixels, what's the distance to this plane? And then just use that as the depth, and you lift it, you unproject this image onto this depth plane. Does that make intuitive sense? So it would look like the thing that you see here on the right. Right, so like this image, you imagine you draw a ray through each of these pixels, and wherever the ray intersects the depth plane, that's where you copy the pixel value. Right? Okay, and now what you can do is you can compute the loss of this warped image at that depth plane with the loss of the other image on that depth plane. So the other image just looks the same, right? This one now looks different depending on the depth. And now you just compute the loss between these two images. So for instance, by just taking the difference, right? And in this case, for this depth plane, it would look like this. So now let's do this for all of the depth planes. What you would expect, right, is that for every pixel where the depth is correct, the loss should be minimal, right? Like the loss should be 0, ideally. Because for every pixel where you got the depth exactly right, like the pixel from the right-hand side image and the pixel from the left-hand side image should have the same color. And so they should give you the correct loss for each of them. Does that make sense? So this is actually a very old idea. This is the idea of cost volumes. We're going to revisit it later when we talk about dynamics and optical flow. And this is a very powerful idea. It's basically the idea of discretizing your search space. and then for every discrete candidate, kind of just computing the cost of like considering that this would be the correct candidate. In this case, we are discretizing the depth space, and then we're computing the cost for each depth, as if we're basically computing the cost as if that was the depth that we wanted to predict. And now it's easy to imagine how you would now go from this to a depth map. You do it by looking at the cost volume from this angle, so exactly like this. And now for each ray, for each pixel in this image here, you just shoot it through the cost volume, and you look at the costs along the ray, and you just pick the minimum cost along the ray, and that is the correct depth. Does that make sense? Okay. So who can explain to me how that relates to the epipolar lines? Other than David. Yeah. So everything until the cost volume, how you build the cost volume makes sense? So like now, let's say you want to compute the depth in this camera coordinate frame. So what you're going to do is you're going to, like one way to think about it is you shoot a ray through every pixel, and then you plot the ray intersects all of these planes, right? And then for each of the intersections, you plot the cost. And that will look something like this, right? And then you can say the correct depth should be, and there's a big asterisk here, but the correct depth should be the depth where this cost is minimal along the ray, correct? Does that make sense? Cool. And now the question, how does this relate to epipolar lines? Yes?
Might be not understandable, but would it be just like for each pixel we're sampling along the epipolar line until it matches?
Exactly. So this is kind of, I don't know if the word dual is the right thing to say here, but it's kind of just a different way of doing the epipolar line search in a way, right? It's exactly the same thing. Like what you're doing in practice here is this cost here would be exactly identical as if you took this pixel, you unprojected, you took the ray that belongs to that pixel, you sample lots of points along that ray, you project these points onto this image, and in this image they will lie exactly along the epipolar line. Then for each of these projected points you compute the cost, and then it would give you exactly this plot. So why would you do this instead of the epipolar line search? One is a very, very practical reason. This is like really easy to implement, and it's very easy to parallelize. Because you have like this discretized search space. It's like, this is very, very easy to implement, while the epipolar line search thing is kind of a pain to implement. And it's like for very practical reasons, which you may or may not interact with in the homework. In one case, when you do this projection business, you like take the ray, right? And then you have to project it. And there's like lots of boundary edge cases that can happen. Like, I don't know, the point that you project is outside of the image space. Or like, and different epipolar lines maybe don't even exist and stuff like that. Like this here is like just conceptually very easy to implement and conceptually very easy to do. And I didn't get, so there's, I pulled these slides from a video, which I encourage you to watch. The link is here on the bottom of the slides, and you can find the slides online. I should have uploaded them before the lecture. I think I did. Are the slides online? Yes, right? Yeah, I definitely uploaded. Okay, good. You know it. Good. So slides should be online. I encourage you to watch this video. There is papers now that, okay, so the original plane sweep stereo paper just really did this via like filtering this cost volume. When I say filtering this cost volume, let's talk about this a little bit more. So imagine you plot this cost. This is kind of an idealized cost. What would this cost actually look like for an actual real-world stereo pair? So like imagine I took my iPhone and I took two pictures, like one picture from here and one picture from here. And now for one of these rays, I would actually show you what this plot looks like. What will this plot actually look like? The cost plot. Well, this is actually a bad image. Let me see if I find another stereo image. No, I don't think I have another stereo image in the slides, but maybe you can imagine. Actually, you have a stereo camera in your head, which is your eyes. So maybe you can imagine what that would look like, right? So your left eye shoots a ray, right? And now you basically project that. You can look at that. You can even look at my finger. So like you can look at your own finger. Obviously, you can't look at my finger from my perspective. But if I stretch out my finger, right, my finger is like somewhat aligned with my left eye, so I can look along my finger. And now I can look at my finger from my right eye. That is kind of the projection of that point on my finger onto my right eye, right? And now you might imagine, if you extend that, you might imagine that you can compute the similarity of the points along the epipolar line in your right eye compared to the color that you see in your left eye. Okay, I'm not doing a good job explaining this. But I think you can still follow me and tell me what this actually looks like in practice. What does this cost look like, you think, if you just compare colors along the ray? It'll look, yes. Yes, it'll look super noisy, right? And why is that? It'll look super noisy because you are comparing, it could look super noisy, it could also be super flat. Imagine, for instance, you look at something that doesn't have any texture. If you look at something that doesn't have any texture, what will this plot look like? It'll basically look something like that, where this is the area that doesn't have any texture, right? Because if you, like my right eye, if I look at this, right, any of these points that I project onto my right eye, they all have the same color. They all evaluate to the same loss, which is 0. So this in practice won't work that well. And the other thing that can happen, exactly as Cairo just described it, is that the loss might look like this. It's like if you have, for instance, consider the texture on this chair. The texture on this chair is always like, it's like beige, and then it's blue, beige, blue, beige, blue, right? And so if you look with a stereo camera at this chair and you try to find the correct depth by like warping, right? It'll basically be like this. Every time you get to beige on the pattern of the thing, it'll be a low loss, and then like for every other time it will be like a high loss. So this is actually not gonna. I mean, this is kind of okay, but it doesn't quite cut it. So the original plane sweep stereo algorithm, what they proposed is let's not take this cost just naively. Let's just smooth it. We're just going to apply a filter. So they're just saying, oh, let's have like a moving average filter. So maybe the moving average filter will make it look smoother, and that's good. That's one way of doing it. Let me just think if we're going to talk about this again later. No, I think that was the right time to talk about it. Now in deep learning land, can we think of another way of doing? So now I think I would be surprised if any of you knew the answer to this. So I might just tell you, but like, yeah, okay, Cairo, maybe some of you have done this before. What would be another way of computing this cost? Nowadays that we have machine learning, what would be another way of computing this cost that might be more robust to these kinds of like repetitive textures or like having the same color? This is a hard question. I would be surprised if you can think about it if you haven't done it before. So like no worries if you don't understand it. But Cairo, you have done it before. Right. So someone not. So did you hear what Cairo said? Cairo said you can, instead of using colors, you can use features. What does that mean? Let's think about that for a moment. When Cairo says features, what he means is instead of using just naively the colors that you get from these two RGB images, imagine that you have a convolutional neural network, for instance, that looks at image 1. You have a convolutional neural network that looks at image 2. And you make it such that they just output for every pixel a feature descriptor. They just output a high-level feature, right? Okay, and now you build this cost volume not by comparing colors, but instead you build this cost volume by comparing features. And then, right, just notice maybe something that necessitates explanation. These other steps here, they're actually all differentiable. Like finding the minimum along the ray, you can build differentiable versions of doing this. So imagine this was all differentiable. So you could just supervise it with a ground truth depth map at the end. So you have like input stereo pair, image, and you have a ground truth depth map, so you can supervise it. So in other words, you have gradients flowing into these features. Then what might these features learn? So what you would expect to happen is basically that these features learn to infer descriptors of the pixel that are robust to things like lighting changes or like view-dependent effects or like, like things like metallic. But you might also expect stuff like this. It could, for instance, be that the feature will learn to encode the distance from the nearest line, for instance, right? So you could imagine that the convolutional neural network looks at this image and then it says, okay, this is the center of the panel. So I'm going to make a special feature that is going to be center of the panel feature. So all of the pixels along the center line of the panel, I'm going to give them the center line of panel feature. And then the neural network, actually this is a great example. Even for this little column, right? I mean, this is a very low resolution image, but you can imagine one of these Roman colors in the real world, columns in the real world, where you have like a repetitive texture, right? You have these columns usually, they kind of usually, they usually look like this, right? So they have these stripes along them, where each of them is like a little bulge. And there's repetitive texture on the thing, right? But even here, maybe the convolutional neural network will count the column or something. It will say, oh, this is the third ridge from the left. And now suddenly, even though the colors are identical, when you compare the two features will be more informative in their distance than the colors might be. Does this make sense? Excellent. This is actually a very important idea, and it'll come up again and again and again. And we'll explain it again later in a better way. But this is, I think, this is a good illustrative example. Yes.
Is the main reason why those features work so much better is because they just have much higher dimensions, so there's much more flexibility that the network can learn? Or is there more than that?
Yeah, great question. So the question is, why would you expect these features to do better? Is the reason just because they're like higher dimensional descriptors? And I mean, the answer is, first order, the answer is no. So like if you, right, because you can certainly think of ways of going from the color to like some really high dimensional descriptor that doesn't have any more information than the color, right? You could literally take every pixel and then multiply it with a 1,000 dimensional vector. Now you have a 1,000 dimensional feature, and it still will be exactly as uninformative as before. But the dimensionality does play a role. The thing that happens is basically that what the convolutional neural network does, or like what these neural networks can do, is they can reason about neighborhoods, and they can pick what features to detect in neighborhoods. So actually the chairs, again, that you're looking at are a great example. If each of you look at the chairs that is next to you, the chairs have, for instance, some of these circles have the same color, but they're actually a different symbol, right? So sometimes it's a cross, sometimes it's a circle, sometimes it's a circle with another circle inside. So now what the convolutional neural network will do is it can, for instance, make it robust to the color by saying, this is a circle with a cross, and this is a circle with a circle around it. And ta-da, you have a discriminative feature. And for that, of course, the dimensionality does play a role, because the more dimensions you have, the easier it is to stuff more and more of that kind of information into your feature. But there's another interesting question that you can ask, which is, do you need machine learning for that? And the answer is actually probably not. You can actually, if you take the color as a baseline, comparing colors as a baseline, you can probably do much better than that by like random filtering. So you just build like random little convolutional filters, which are like 5x5 filters or something, and you just initialize them randomly, and then you're just going to convolve 1,000 of these random filters with your image, and then you get a 1,000-dimensional feature like that, and that will probably also be much more robust than the color, just because now it takes like local information into account. So good question. Any other questions? Did that explanation make sense also? Kind of. Great. Oh, good. Okay. So there is a paper that basically what we just discussed is a paper. Like what we just discussed was a paper from 2021. It's a paper here from MIT, which unfortunately I didn't have time to put on slides. This YouTube video is an amazing explainer, so I really encourage you to watch it. And it's an ICRA paper from 2021 from Nick Roy's group here at MIT, so you can go visit him and talk to him about the paper if you so wish. And it's a really good paper, and the YouTube video is amazing, so I encourage you to watch it. Okay, so yeah, so this was a slide that I wanted to remind myself with, like how is this related to epipolar lines? We already discussed that. How is it related to epipolar lines? And here's now a paper that is also from 2021, which exactly visualizes this aspect of this being kind of like you can either view it through the plane sweep stereo perspective, or you can view it through the perspective of search along the epipolar line. This is this paper from Andrew Zisserman's group at Oxford, who is the guy who formalized all of this like intrinsic, extrinsic camera parameter business. Fantastic. He still writes fantastic papers with this research group. So we're not going to talk about this model in depth, but you can kind of, this is the first figure in the paper, and you can kind of get the idea of what this model does. It takes as input two input images, right? And then it produces as output the depth map. And this is a supervised model again, so it assumes that you have supervision in form of the ground truth depth. And now we're not going to talk about what this model does, but maybe you can kind of figure out what the core contribution of this paper is by looking at the title and by looking at this figure. The title is Input Level Inductive Biases for 3D Reconstruction. And then they say this is a generalist perception model. What that really means, it's a transformer. And what this is, this looks a lot like epipolar lines. So what this paper does is basically the following. It says, okay, if we want to get the depth of this point here, what we're going to do is we're going to just build a transformer, and transformers have this thing which is called positional encodings in them. And positional encodings in this case would mean that for every pixel or for every patch in one of these images, you would concatenate it with like an encoding of where that patch is in the image. So at the top left, it will be one value. Like imagine it's just you concatenated with the image coordinates, for instance, with the pixel coordinates. And what they're doing in this paper when they say input level inductive biases is they're saying, okay, I'm just going to tell the transformer that when it looks at both of these images, for this point, the points that it should most look at are along the epipolar line in this other image. So I'm just going to tell it for this point, if you want to compute the depth of this point, these are the points along the epipolar line in the other image. And then what the transformer will learn is it'll learn to look at the points along the epipolar line to figure out what the correct depth should be. Cairo, yes?
This can only be done for points seen in both images, yes?
Aha, that's a great question. So here you, this is just epipolar line. So this is pulled directly from the paper. So this is, you have seen this before. This is exactly the plot that we have in our other paper, basically. This is just explaining a little bit more on how you actually encode it such that the transformer can make sense of it. So the question that Cairo asked was, you can only do this for points that are visible in both images. But this is now kind of the beauty of deep learning. So let's say you do the stereo depth estimation business. Okay, let's say we do this plane sweep stereo. What would you expect to happen for points that are not visible in both images? And first of all, let's think about why that might happen. Why might it happen that a point is not visible in both images? You know this even from your own eyes, right? Like I'm looking at this chair right now. There's an armrest. If I close my eyes, some points are occluded in one eye and some are not, right? Because these have slightly different positions. So some points are visible only in one eye. So what do you expect to happen if you build this cost volume and you try to do that? What will happen? Was that were you considering raising your finger? Oh, I see. Sad. I mean, it's not a very interesting question in a way. It's like, I mean, nothing will happen. You don't know what's going to happen. I don't know. You're going to match it to some random point along the depth is what's going to happen, right? So you have no idea what's going to happen. So how could you counteract that a little bit? You could say, well, I could make sure that when I look at, when I map out the depth, when I map out this cost function for this ray, maybe instead of just going to the minimum for this one ray, I'm actually also going to look at the neighboring points in the image. And I'm going to like somehow make sure that the depths that I'm estimating for neighboring pixels are similar. And then what might happen is if there's points that are occluded, you might expect that instead of giving it like completely random values, maybe you'll give it values that are kind of smoothly extending the values in that neighborhood or something like that. Okay, but the beautiful thing with transformers and all of this deep learning business is that the transformer will just do that for you, right? So what will happen with the transformer? Okay, you're not actually like this transformer is looking at both of the images at the same time. It's seeing completely both images. Now you're just telling it some additional information. You're just telling it, oh, these are the points that are along the epipolar line for these respective pixel coordinates. And so the transformer can just learn that. The transformer can just be like, I guess this point doesn't have a correspondence in the other image. But actually, I have the ground truth depth for this point. I've seen at training time, I have seen points like that, and I have their ground truth depth because, for instance, you measured the depth actually with a depth camera instead of like computing it from the stereo. And so then the transformer can just learn rules like that. The transformer can just be like, oh, I'm just going to inpaint the depth for this point, even though there is no correspondence. So the transformer can basically fall back to monocular depth estimation, for instance, for all the points where there's no correspondence. Okay. Yes? You have scaling? Did you ask this question about it? You asked about scale? Sorry.
No, so you mentioned that like the transformer model can inpaint the depth.
Yeah.
And so like inpainting is
Yeah.
model hallucination.
Yeah.
Then how would you know that like the scale that it's getting back out is correct?
So like, yeah, the only way you could train your transformer to do this kind of inpainting is if your ground truth depth would have depths for these values. And the reason why that might be the case is because, so in this data set, that's certainly not the case. You can even see it, that all of the things are black wherever the point is only visible in one view. but you could imagine that you have a stereo rig. The way you captured the data set, you have a stereo rig, and then you also have a depth camera on top. And so the way you computed the depth could actually be different than stereo depth estimation. Or you do it via structure for motion. But in practice, that doesn't actually happen. It's just kind of a... And also I realized I'm actually apparently talking too much, because I have actually another exciting topic, which is slightly more exciting than this, which we're going to get to now. So, and I really want to get to it today, so we're going to go through the rest in a little bit of a speed mode. Who knows what a normal map is? Okay, so almost everyone knows what a normal map is. Just for the record, the normal map is if you look at a point in the 3D scene, it's just the direction vector of the surface normal of that point. So, in other words, it's the in fact it's the derivative of the depth map. So if you take the depth map and you take the finite elements derivative of the depth map, so you derive it by dx dy. So you take the depth and you just compute basically the difference to its neighbors. What that will give you is exactly the surface normal, turns out. Okay, so one thing that is interesting, which we're going to just briefly say, because I saw this paper back in the day and I thought it was really neat, you can think about what is easier to predict. Is the depth easier to predict, or is the surface normal easier to predict? And there are, of course, different things. Like you can't easily, if I give you the surface normals for an image, it's not straightforward to compute the depth from it, because clearly the depth, if the surface normal is the derivative of the depth, then of course the depth is the integral of the surface normal, so you would have to integrate the surface normals, and that would give you like the relative distance depth. So they're not the same thing, but it turns out that computing the surface normal is much easier than predicting the depth. And why would that be the case? It's just something to keep in mind, and we're going to come across it again later in this course. The reason why that is if you think about, now we are back in monocular depth estimation land. So if I give you a single image, so not stereo, I give you a single image, and from that single image, for every pixel, I ask you to predict either the surface normal or the depth. Let's think about what the neural network has to do to predict the depth. What are you doing if you close one eye and you look at the scene, and your brain is clearly estimating the depth? What is it doing? There is no multi-view information in this, so the only way your brain can estimate the depth is by experience. So what your brain actually does is it looks at things like the vanishing points. So it looks at like the angle of the vanishing points. It looks at things like scale. So this chair is close, this chair is further away. It looks at things like occlusion. So this chair is occluding this other chair, so probably this chair is in front of that chair. So it's using all of these like tricks that are informative about the depth. Let's talk about scale for a moment. So one very good hint is the scale. So this chair is much closer to me, so it's much bigger. This scale in the back is much smaller, right? So in other words, imagine you have seen this bottle before. One really good way of estimating depth is remembering how big that bottle is, and when you see it in an image, you're like, oh, how small is it? And that's going to tell you about the depth. But why is it then that, why is that a hard task? It's a hard task because estimating the scale requires you to look at like the context of the whole image. Like if you want to get this, if you want to estimate the depth of a point, you have to look at the depth is not a local property. Like in other words, if you want to estimate the depth of this something that the bottle. If you want to estimate the depth of this bottle, it doesn't suffice to just look at the local neighborhood of this pixel. You actually have to look at the whole neighborhood that contains the whole bottle, because you have to estimate the scale of the whole bottle. That's the only way how you can get the depth of this pixel. The surface normal is different, because the surface normal is a local property of the scene. So in other words, to predict what the surface normal of this point looks like, you might not have to actually reason about the scale of the whole bottle. It might suffice to just look at the local neighborhood of the pixel. And so it turns out, what does that translate to? It turns out that that translates to surface normal prediction being much simpler. So this paper basically is a cool paper. I saw it at a conference some time ago. And they basically just train surface normal prediction, and they show that it works quite well. And then they do this funny little experiment. They take an elephant, and they place the elephant, they just Photoshop it on top of this scene, right? So what do you expect would the monocular depth estimation network do? The monocular depth estimation network will just give up. There's no way it can figure out what is happening here, because it doesn't make any sense, right? Like the monocular depth estimation will be like, oh, this is an elephant. I don't know, even if there are elephants in the scene, like how big is this elephant? No idea. And certainly the scale of this elephant doesn't make any sense compared to the scale of the room that's in. Makes no sense. However, if you predict the surface normals are a local property of the scene. So the surface normal, it can predict the surface normal of the elephant and the room that it's in just fine, because it doesn't have to reason about the global scale of the whole scene. So this is just a really neat little thing that is interesting to be aware of. So sometimes it's unintuitive how big of a difference it makes to just like switch modalities a little bit. And maybe all you need is surface normal. Okay, good. Cool. So now we're going to get to an exciting problem. So there's this big problem that the depth that we're predicting so far, all the depths, all the models that we discussed that do supervised monocular depth prediction and supervised stereo depth prediction, they all use the scale invariant loss. And these scale invariant losses are great because they allowed us to make these really impressive depth maps. The problem, of course, is that the neural network has not actually learned to predict the correct depth at all. It has just learned to predict the correct relative depth for each pair of pixels in the image. And in practice, that is maybe not what you want. Imagine you want to build a robot, and the robot should grasp something in the scene. What do you actually need? Well, it turns out you actually really need the metric depth. It's not good enough to just predict this depth with this random scale, right? So there's an interesting paper which I'm just going to refer to. The method is not that fundamental, so we're not going to talk about the paper. But this paper, basically what it proposes to do is it says, oh, we're going to pre-train a relative depth estimation network in exactly the way that we just discussed. And then we're just going to build a little fine-tuning scheme that uses very few parameters on top of that network, such that we can just calibrate it to predict metric depth. So it's kind of just like, oh, we have very little metric data. We have lots of not metric data. We're just going to train something that does relative depth estimation on this big data set of relative depth. And then we're just going to fine-tune it a little bit on this metric data set in a smart way. And then this thing actually does approximately output metric depth. This is a paper from 2023. So getting pretty close to today. And this is actually, I don't know, has anyone used this paper or seen this paper? I haven't used it myself. I don't know how well it works, but I have heard people say that it works surprisingly well. So it might be worth a shot. Okay, good. Here's, and now we're getting to the favorite part of this thing, even though we have just 20 minutes left. So this is a paper from friends of ours at Cornell. So Bill is, of course, at Google and at MIT. So Bill is a professor here. Noah is at Cornell. Zhengqi, I don't know where he is right now. Tali is now a professor in Israel at the Weizmann Institute. So these are all well-known names in 3D computer vision. You'll come across them very often. This paper did something funny, learning the depths of moving people by watching frozen people. So let's talk a little bit about this part where how do we collect these data sets that allow us to train these monocular depth estimators. And there is a little bit of a problem with that. So far we said, what are the different ways of collecting these data sets? One is we have RGBD sensors. Okay, obviously if you have an RGBD sensor, you can run around in the real world and you can collect ground truth depth. What's the problem with that? It's actually really hard to collect big data sets like that. And when I say big data sets, I mean internet scale. YouTube doesn't have depth, right? And why doesn't YouTube have depth? Because all the cameras that people used to collect YouTube videos are novel cameras. That may change in the future. You'll get more and more data with depth because modern phones have depth sensors in them. Like this phone has LiDAR, crazy. But for now, we're stuck with this. So RGBD cameras are not good to collect internet scale training data. So what many of these data sets use that we saw earlier, they use structure for motion. Structure for motion, like CalMap, like the stuff that we discussed in the third lecture, is seemingly a great candidate for collecting large-scale depth data, right? Because you can just download all the videos from YouTube, then you run CalMap on them, and then CalMap will give you depth for all of these videos. Okay, of course, 20% of the time it doesn't do anything, and then you're okay, that didn't work, but you just throw these away. I don't know, it doesn't matter. You have 100 million videos, just throw away 20 million, still have 80 million, great. Okay, problem though is another one, which is that structure for motion doesn't work. We discussed it shortly for dynamic scenes. Because this whole shenanigans of matching correspondences, it assumes that the only motion in the scene is the camera motion. So it doesn't work for dynamic scenes. So let's say you want to build a monocular depth estimator that estimates the depth of people. You're all sitting here, and now I want to take a picture of you and I want to put it into my monocular depth estimator. What will happen? It'll give you garbage. Why is that? It's because in 99% of the scenes, that you reconstructed the structure for motion, the depth of the people was wrong, or it just failed. So you have a very, very few data where you have correct depth estimation for people that are moving. So this paper did something cute. There was this cool challenge, I don't know, this was 6 years ago where all this flash mob stuff was a thing. It was called the mannequin challenge. Does anyone remember the mannequin challenge? Okay, I actually don't, but maybe I'm too old. I don't know. So the mannequin challenge was people were like standing around and acting as if they were frozen. I forgot to put the video in. Oh, anyways, you should go watch the video of this paper. And like, people are frozen, and then people walk around with a camera, and everyone's acting like a mannequin. Amazing. We can take that, run structure for motion on all of these videos, get depth for all of the people that aren't moving, train our monocular depth estimator, and now it will work if people are, even if people are moving, because it's done in monocular depth. Great, right? Great. So I thought this paper was really cool, and many people thought so. And it is a fantastic paper, but of course, if you think about it, it's kind of a joke. Like the fact, okay, so is that really the way we're going to do it? Is it really like we're just going to, okay, like the problem is this, the way we're going to solve it is we just have everyone do a challenge, and then like we can collect this data. Obviously not, right? I mean, amazing that this worked in this case. It really did work. It was great. But the problem really is fundamentally things are moving, and we can't generate multi-view stereo reconstructions for things that are moving. In other words, if structure for motion were a solved problem, this would be a great data source, but structure for motion isn't solved, so we're stuck with this. Okay. Bad news is it's still not solved. Maybe one of you will solve it, or maybe we will solve it here at MIT. Still not a solved problem. But now we're getting into territory of like ways in which one might think about fixing this problem. Okay. Okay. Now we're going to talk about unsupervised depth prediction. So far we just did the boring thing, which is we collect a data set of ground truth depth, and now we just train our thing to like predict the depth that we collected. Is there a way of doing it without ground truth supervision of depth? And the answer is yes. So the goal is, this is actually a bad example. So imagine you had a video in which nothing would move. Okay, so here's their stuff moving. But imagine you had a static, like a video where only the camera is moving, everything else is static. The goal is the following. I'm going to give you a data set of videos like that, hundreds of millions of videos like that. Can you, just from these videos, without having the camera poses, without having the depth, train a neural network that predicts the depth from a single image? The answer is yes, and the question is how. I'm throwing this up here one more time. One key part of this will be this notion of unprojection. So go from pixel and depth to a point in the 3D scene. We have belabored it a few times by now, but if you still have questions about it, now is a good time to ask it. So it's just this idea. If you have the depth of a pixel, you can like lift it to 3D to a point cloud. Now, the second thing we're going to talk about, we already suggested it, is there's this idea of depth warping. And in many ways, this is the dumbest way of doing neural rendering, or the simplest, I should say. This is the simplest way of doing what we will call later differentiable rendering. The simplest way, what is differentiable rendering? Actually, we're not going to get into that right now. But the task is as follows. I give you this view and its depth, and I ask you, what would this 3D scene look like if you looked at it from a different view? Okay, and how can you answer this question using the depth map? The way you can answer this question using the depth map is like conceptually, although in implementation you would do it differently. Conceptually, you take all of these points, you project them, you lift them, you unproject them into 3D, right? You make a point cloud out of them. And then you have these points in 3D. You take this camera view from here, you project these points back onto the other camera, and then you just like plop the right color in that point. Does that conceptually make sense? So basically you can just render the depth map, you can render the point cloud from a different camera position. I think you're doing that in, is this part of homework number 1? No? It's probably part of homework number 2. Have fun. But does that conceptually make sense, how that works, right? And so does it make sense why there's black shadows here? These are the points you haven't seen, right? These are the points that are occluded from this camera's perspective. So like you haven't actually seen this point in this camera, so it's black. Does this kind of make sense intuitively? Okay, good. Now, how can we use this for training a depth estimator? Okay, here's what we're going to do. So this is the first self-supervised model that we're going to talk about, but it's not going to be the last, but the first. We're going to take 2 frames of a video. Right? I give you a video like this. This is a video from the KITTI dataset, or the self-darting dataset. I give you 2 frames of a video, and we're going to call one view the target view, and one view, they call the nearby view, let's call this the context view, doesn't matter. Now, we're going to build a convolutional neural network, or transformer, doesn't matter, and we're just going to say your job is to predict the depth. So for every pixel, you're just going to give me the depth. Makes sense, right? We discussed this before. Just note that right now, this is not going to be supervised, so you're never going to show this thing a ground truth depth map. but you're just going to say, I'm going to interpret the output of this network as a depth. Make sense? Good. Okay, so this is your depth CNN. And now you're going to do something funny. You're just going to take these two views, you're going to concatenate them, and you stick them into another neural network, and you're going to be like, your job is to predict the camera pose. So your job is you take frame number 1, frame number 2, and you're going to tell me how the camera has moved. So intuitively, that is definitely possible, right? If you look at video, if you watch a video, you'd know how the camera has moved. So you know it's possible. What the neural network is doing, this paper didn't think about too much because it's kind of unclear. But you can definitely think of like ways in which the neural network might try to solve this task. It'll like look for like, I don't know, one way you can think about it is like if the motion is small, right, then if you concatenate the 2 frames, then like you'll see that an edge has like maybe moved a little bit from frame 1 to frame 2. So you can like look at the angle of the edge and then you can say, okay, probably the camera moved to the left, something like that. So, but we don't know, we don't care. This is 2017. We just stick everything into neural networks and pray it works. So here, this one, we tell it, you predict the camera pose between these 2 views. By the way, this is literally the reason why I'm standing here today. This is the paper that got me into 3D computer vision, which is also co-authored by Noah, who's the other guy. So this was the paper that I read, and I was like, this is crazy. We're going to do more of that. Okay, so now how are we going to supervise this? Because we don't have neither ground truth poses, nor do we have ground truth depth. What we're going to do is we're going to use the pose and the depth to ask, like this view that we have here. Actually, no, like, okay, vice versa. We take 3 frames of the video. One is, so this is the frame at time t. This is the previous frame. This is the frame that comes afterwards. And now we're going to say we have the depth for that frame. Please render this view, like given this pose and this depth map, produce an image like what we saw here. Do this for the frame before and the frame afterwards. So basically, take these points, lift them into 3D, and use the pose to like ask how would this scene look like from this other angle if the pose and the depth were correct. Does that make sense? Yes? Not? Questions? Discussions? Fears? Good. Yeah, makes sense? Good. So this is kind of nuts. So just repeat. So basically, we have predicted the poses from this view to this view and from this view to that view. And now we're going to use the depth and this pose to synthesize this view using the depth map. So we take, this is the target view, so this is the view at the top. We're going to use that view. We're going to generate these 2 things. And then, what do you know? This is all differentiable. Nothing weird going on. We're going to have to talk about why it's differentiable in a moment. But this is all differentiable. And then how do you train it? You just train it by comparing it to the true image, which you do have the true image. You don't have the true depth map. You don't have the true pose, but you do have the true image. And so turns out you can like train that. You just use lots of videos. You need nothing else other than the camera intrinsic parameters. You need the camera intrinsic parameters. But if you have the camera intrinsic parameters, you can just train this whole thing on a big video data set, right? Cool. So one reason, like, how does this depth warping actually work? And this is mostly, I think, if you really want to understand this, you probably have to implement it yourself, or you have to like read the paper yourself. But I just want to give you the idea, why would this thing be differentiable? Why would the thing be differentiable that like generates this new view of using the depth map and the color image, right? And the way this works in practice is the naming here, I don't love the naming too much. Is it like a stick that I can use to point? Apparently not. Oh, well. Okay. So I hat S is in fact, so I would call this I hat T, but I hat S is in fact the view, this view here, this image, IT, generated using warping. So this is the target image. IT, right? IT is this image at the top. IT is the image at the top. And IS hat is that image regenerated using the depth map and the pose. So this is like you're re-rendering this image. You're asking, you're using the pixels from this image to re-render this image. And how does this work? Long story short, the way it works is you use the scary looking equation, which you can probably recognize what it is. Take point, k minus 1. What does k minus 1 do? unproject, exactly. So this maps point to ray, then multiply by depth, which is the predicted depth. That unprojects the point to 3D. What is t? T hat is poorly named, but this is the camera, like this is the relative transformation of the two cameras. So this is kind of cam to world, you can imagine. This is cam to world, and then k is project onto the other view. So this is basically lift, lift, change camera view, project, right? Okay. So that's what you're going to do. You take the you take a pixel coordinate from the target image, you lift it using the depth map, you transform it using the camera pose that you predicted, you project it onto the onto one of the other two views, right? So you're lifting this point to 3D, you're translating it using the pose that you predicted, and then you project it onto this camera, for instance. Make sense? Okay, good. And then how do you? The problem is kind of that, like, now what you want to do? Now what you want to do is you want to ask, what is the color at this point? Because now I can take that color and I can compare it to the color in this image, and that's my loss, right? Make sense? Okay. So how do you get the color? The problem is that the pixel that you have, the pixel is not going to fall exactly on one of the other pixels, right? It's going to fall somewhere in between. It's going to be some real valued, like, floating point number. So what you have to do is interpolation. So bilinear interpolation. You take the 4 closest pixels and you bilinearly interpolate them to get the color of that pixel. Do you know what bilinear interpolation is? Yes? No? Who doesn't know what bilinear interpolation is? Good. Excellent. Where do you learn about bilinear interpolation, just out of curiosity? What would be the class at MIT where you would learn about stuff like that? Okay, good. Okay, good. So I'm asking because then I don't have to explain it, which I like. Okay, cool. And then, so this is bilinear interpolation, and then the loss is just, so this is the target image, and this is the target image re-rendered using the depth map and the pose, predicted pose, using the pixels from one of the other two images. Okay, I think we're kind of running out of time, so I'm going to keep it short. This is, long story short, you can just train this. There's more things like multi-scale loss and so on, which we're not going to talk about today. I'm going to talk about it in the next lecture because I love talking about this. This is the depth that you get out of this. You know, so it looks like from 9 years ago with supervised depth estimation, kind of, right? Okay. But remember, this paper is from 2017, so that's from 6 years ago. Of course, things have changed. People have worked on this a bunch. And this is kind of what this kind of stuff looks like today. This is the input image. This is the output depth map. And this is the re-rendered point cloud from a slightly different camera angle. And you can see there's still like some weird stuff going on, right? Like stuff is popping in and out of existence and shenanigans like that. But like overall, if you look at these depth maps, pretty neat, right? So this is without any supervision, just video. Okay, problems with this, it can't deal with occlusions and disocclusions. So like this very simplistic way of doing what we call novel view synthesis, of like asking what does the scene look like from a different angle. It can't deal with occlusions and disocclusions, so that kind of sucks. It also can't deal with things that are moving. And what happens if you try to train these kind of things with things that are moving, you kind of can't see it, but it just puts a hole at the position where the car is. It's just kind of just like, okay, I don't know. Put a hole there. And this is this paper we're going to discuss next time. What are the techniques to solving this? And then we're going to talk about other stuff afterwards. But this was the first deep learning lecture we had. And yeah, thanks for listening. I hope it was interesting. See you next time.